Okay, welcome back. Today we're going to be looking at Chapter 2, Linear and Quadratic Functions, looking at Section 2.2, Absolute Value. Absolute value, you probably are familiar with the idea that absolute value just turns a number positive. You may have also heard distance from zero, and distance from zero is a good way to visualize what's happening. If I have a number line drawn, and I have a couple of numbers, let's say 3 and -3, then I see that both of them have the same distance, 3, from 0. So the absolute value is the distance from 0. This isn't always practical when solving equations. Turning a number positive is another good way to think about it. If the number is negative, then the absolute value will turn it positive. But in what way does it turn it positive? Well, the easiest way to do it is by multiplying by -1. I multiply a negative number by -1, then I'll obtain the corresponding positive number that's the same distance from 0. We can think of this simply as a reflection across 0. Transformations coming into play once again. Therefore, what I will have here is the absolute value of x, denoted by these absolute value bars about x, can be given as a piecewise function where if the number is greater than or equal to 0, we simply do nothing. And if the number is less than 0, we will multiply by -1. What this ends up giving us in terms of a graph this top part, y equals x, and this bottom part, y equals -x. Both of these are lines with the intercept at the origin. The first one has a slope of 1, the second one a slope of -1. They would continue if we weren't looking at piecewise, but what we actually end up with is this v that you might be familiar with. It's simply two lines intersecting at the origin. Notice that everywhere, while the x value could be positive or negative, the y value, it's always positive. Now, there's a couple of nice rules that I get with absolute values. The first one is that if I multiply two numbers, it doesn't matter whether I apply the negative before or after multiplying them, as long as I apply it to each piece. So I can do the absolute value of two different things if I'm multiplying or dividing, or even if I'm doing an exponent, which we know is simply multiplication several times. When I'm trying to solve equations with absolute value, the interesting question happens if the function is equal to a positive or negative number or 0. Because the absolute value has a range of greater than or equal to 0, I can actually never solve it if the absolute value is equal to a negative number. If the absolute value is equal to 0, then there's only one solution. But if it is positive, then I have two solutions. Think of the two different halves of the v. If it's negative, I have no solution at all. This IFF is shorthand for if and only if. So for example, I can read this second line by saying if c is greater than 0, then the absolute value of x is equal to c if and only if either x is equal to c or x is equal to -c. Let's go through a couple of examples here. Suppose I have 3x minus 1 is equal to 6. Now I'm going to need to solve both halves of this. 3x minus 1 could be equal to 6, or 3x minus 1 could be equal to -6. Both of these will be valid solutions. Because if the inside of the piece was equal to 6, then the absolute value would leave it alone. And if the inside of the piece was equal to -6, then the absolute value would flip it, turning it to +6. So we'll quickly solve each side. 3x is equal to 7, or x is equal to 7/3, and 3x is equal to negative 5, or x is equal to negative 5/3. Once again, both of these are valid choices, so we will report the final answer as x is equal to negative 5/3, 7/3. Separating the answers by a comma indicates the fact that we want both answers to be viable choices. Let's go through another example here. This one is more complicated because there are more pieces going on. It looks like it's been transformed many times. In order to approach this equation, what we'll need to do is first isolate the piece with the absolute value and then solve. So I will first subtract 6 and then divide by 3. Notice now that what I have is an absolute value equal to a negative number. This is not possible. There's nothing I could put in that when I take the absolute value of it will turn it negative. So I will simply say no solution. This example looks a little bit different because what I notice is that there's a variable on both sides. So isolating the absolute value is helpful, but I'll need to do more. I'm going to split it up into two pieces where I have x minus 2 is equal to x minus 1, and then also x minus 2 is equal to negative x minus 1. I'll need to be sure in the second piece that I put it in parentheses to indicate the fact that the entire thing would be flipped in sign. Now I can simply solve each side. On the left-hand side, what I will get is x minus 2 is equal to x minus 1. The first thing I would want to do is I want to move x to both sides. In subtracting x, I get negative 2 is equal to negative 1. No solution. But that doesn't mean there's not a solution to the entire thing, because the second piece we may be able to solve. Here, after distributing this negative, I can add x to both sides. Then, after some quick algebra, x is equal to 3/2. Now, the reason graphically that this has no solution is that my first piece, absolute value of x minus 2, thinking about transformations, this is my absolute value graph shifted over to the right by 2. Let's make sure I'm labeling my axes so that the graph is clear. And actually, sorry, we should make sure this part is clear as well. There we go. That looks pretty good. So this represents the graph of x minus 2. The other piece, x minus 1, is simply a line with an intercept of -1 and a slope of 1. We see that it intersects the left half at our solution of 3/2, but it never intersects the other side. This is why we only getting one solution. Now, we've seen the graph of y equals absolute value of x before. What we would like to be able to do is use everything we learned in the section on transformations to be able to change this graph up. Here, I have y is equal to 4 minus 2 times the absolute value of 3x plus 1. Let's take a look at what this would end up looking like. So if I graph this, what I notice is that I have several different shifts and stretches and also a reflection. Let's rewrite this in a form that more clearly identifies each piece. -2 times the absolute value of 3 x plus 1/3 plus 4. We've rearranged this to more clearly show the shifts and the stretches. So let's identify each piece. This plus 3 is a shift left by 1/3. Recall that the addition indicates that it's a shift to the left rather than one to the right. The plus 4 is a shift up 4. Next, we can identify any stretching. This 3 is a shrink horizontally by a factor of 3. So it will be 3 times as skinny. The 2 indicates a stretch vertically by 2. The final piece is this negative. The negative will be a vertical reflection. Vertical because it's applied outside, not directly to the X, but to the entire piece. All of this together will allow us to graph this function. Once again, I like graphing this in pieces, and then we can isolate the final answer on a separate graph once we're done. I'll begin with the original absolute value of X. And let's plot the origin and a couple other points so we can more easily track the transformation. I like to do both of the stretches and shrinks at the same time as the reflection. So horizontally, I will shrink by a factor of 3. Vertically, I will reflect and stretch by a factor of 2. This means after any stretches and shrinking, I will obtain something that looks a little bit like this. This point 1, 1 has now become the point 2, negative, 1/3, negative 2. Horizontally, I've been shrunk by a factor of 3. Vertically, I've been reflected and stretched by a factor of 2. The other point has undergone a similar change. The origin is always unaffected by stretches and shrinks, but it will be affected after we do our next change, which is a shift. Make sure you track the shift through the vertex of the absolute value, as this will be the most important point to graph, as this is where the graph changes direction. We're shifting left by 1/3 and up by 4. So the new vertex will be the point negative 1/3, 4. I can then graph each of the other points as they changed as well. This 1/3, negative 2 will now become the point 0, 2. And over here, negative 2/3, 2. This gives me my final graph, which I'll redraw on the side to isolate it more clearly. Going through negative 1/3, 4, and then having the point 0, 2, and negative 2/3, 2. Okay, that's all we have for this section. See you guys next time.